Yeah, so I teased this a little bit. So normally we would go to a rice table once we kind of start to understand how to handle a buffer system. Well, there's an easier way, and this only applies to one-word equilibrium. It only applies to when we know certain things, but we can at least exercise our math skills a little bit and make our life easier. Let's take the equilibrium expression. Ka is equal to a hydrogen times conjugate base divided by acid. They're a regular old machine here, and I want to solve it for hydrogen ion concentration. Okay? When I do that, I'm going to distribute back through this information that's going to leave me with this. This value gives me hydrogen ion concentration, but I want to solve for pH. So let's negative log the whole thing. Negative log the whole thing yields negative log Ka minus log of acid over anion concentration is equal to negative log of the hydrogen ion concentration. This looks familiar, I hope, to you. This has potential to be familiar to you. This, not so much yet. So let's see what happens. This is what we came up with on the last page. Because negative log Ka must be pKa, negative log of hydrogen ion concentration is pH, and negative log of HA over anion is equal to positive log of anion over HA, we can rewrite that whole formula, pKa plus the log of the conjugate base and the intact acid is equal to the pH. pKa is often given for our weak acids. It's easy to get, and we aren't supposed to remember it, so this is a freeb. These two concentrations are equilibrium concentrations. If we know these three things, then we know pH. Okay, a straight shot at pH. So let's look at that expressed wholly and alone here. This is called the Henderson-Hasselbalch equation. This is a new tool for you. It is very useful, but it is not the only tool. Do not lean on it, and I'll give you some parameters for its use soon. And I've reiterated here conjugate base acid. Let's say you're looking at a basic system. It looks a little bit like this. pKb is equal to positive log of the conjugate acid divided by the base is equal to pOH. Okay? Sorry, conjugate acid divided by the base. I'm not sure I said that right, but it's written properly. We can use both of these at equilibrium to help determine a pH a little bit more rapidly than we had so far. When can you use Henderson-Hasselbalch? When some combination of those variables are there at equilibrium, that's important, and or you can derive them and you have to calculate the fourth one. When you can't, when things aren't at equilibrium, when pH is not part of the question or the answer, or any other time. And seriously, please don't fall in love with it. One of the mistakes we see students make is they jump back to Henderson-Hasselbalch when they don't know what to do, and almost always that's a huge mistake. So here's a set of hints for handling a buffer question, and we'll jump through this pretty quick because we'll say these words as we work problems. We have to figure out what the major systems are in a system at the start. If you added an acid or a base, you're going to find moles of each, and we're going to react them. React means use some stoic to determine what's left over. It's sort of a quick way of doing a limiting reactant, kind of. Seeing what's left over, then putting that leftover stuff, if necessary, into an equilibrium, and then doing calculations. You'll see us use a before change after chart. Before change after is not rice table. It's basically just making sure we know what's reacting and what's left over afterward. And then we'll convert into molarities and build a rice table so we can find equilibrium concentrations. Then we can do our Ka setup. Or now that we have this new tool, the Henderson-Hasselbalch equation. And always at the end, we're going to check logic. So here we go. A solution is 0.12 molar in acetic acid, 0.09 molar of sodium acetate. Calculate the hydrogen ion concentration at equilibrium. The Ka is that. This is not yet a buffer. We're making a buffer, and we're going to figure out the concentration. From video 1, we did one very similar to this, so let's whip through it. We're just setting up the buffer. There's no acid or base being added, so no big deal. Here's our reaction, and there's our initial concentrations. We whip through all that. We get our equilibrium expression. We neglect x's equal to our Ka. Negative log, 2.4 times 10 negative fifth is our equilibrium hydrogen ion concentration. So we had the hydrogen ion concentration asked for in the question. If this wanted a pH, we would negative log this and find the pH, but it didn't, so we won't. Moving on. A solution is 0.12 molar in acetic acid. This is the same conditions. We are going to show you how to use Henderson-Hasselbalch to do the same thing we just did here. So rather than plug and chug into all this and neglect x's, go directly to Henderson-Hasselbalch. You have the Ka, the pKa, that's the negative log of that. There we go, that's 4.74. Then you put in your ratio, 0.9 divided by 0.09, pardon me, divided by 0.12. Log that. It's a negative value. Removed from 4.74 gives 4.62, which is your pH. 10 to the negative 4.62, 2.4 times 10 to the negative fifth. Now, both of these ways, to many of you now, are going to seem fairly straightforward, and that should be the case. So let's get going. The challenge with buffers is knowing what you have and determining what the system's properties are after things come back to equilibrium. So, same buffer system, but we now have 100 mils of 0.1 molar acid being added to a 455 milliliter solution of your buffer. Now, your head's spinning, relax. We got to do some stoic first. Note that you have 0.1 liter and 0.1 molar, so we find how many moles we have of hydrogen ion being thrown at our buffer. We then take our buffer system, 0.455 liter of the buffer system, times, we know it's the acid, by the way, is going to interact with our conjugate base, times the molarity of our conjugate of our buffer system, and we get the number of moles of acetate present. Now, you might say, well, this is a 1-to-1 ratio, so wouldn't these just react in a 1-to-1? Yes, they do. And so then we're going to, and this is, by the way, we need to know the molarity, the number of moles of our intact acetic acid. That's going to allow us to fill in our before change after. So these are the number of moles of intact acid. This is the number of moles of acetate ion. And we would expect the acetate to attack this acid to neutralize it. So let's see how we write this before change after. These are the values we just calculated in terms of moles. When you're doing these relationships, it's easiest to work with moles because the volumes are going to be changing when you add these things together. So it's easier just to go to liters later, or to molarities later. Initial values, we know that this is the smaller substance, and there is more of this. They react in a 1-to-1 ratio, so this all gets consumed where 0 acid is left. We still have some of our conjugate base, and we have added this much of our acid. And so we now have an acid number of moles, and we have our conjugate base number of moles. Now, we're not at equilibrium yet, so don't start thinking that. All we've done is react our acid with our buffer system. In doing so, we now have the number of moles of acetate divided by the volume to get a molarity of our acetate. We will take our number of moles of acetic acid divided by the total volume of the solution to get the molarity of acetic acid. So now we have 2 molarities to begin. This is our initial values to put into our equilibrium system. Okay? So we then set up our molarities into our equilibrium system. Here's our initial set. 0.116 molar acid, 0.0559 molar acetate ion. We lose some quantity of that. We gain the equal molar quantities of these two things, and we set up our Ka expression. Again, we neglect our x's, and we solve for hydrogen ion concentration and get a pH of 4.427. Now, you might say, what about Henderson-Hasselbalch? Here's our pKa value here. We plug into Henderson-Hasselbalch with our ratio of acetate ion to intact acid, and we get the same exact pH. So this note, when we use Henderson-Hasselbalch, is the same point at which you would plug things into your equilibrium expression. What's new and challenging about buffer systems is using your buffer, determining what remains, getting it into a molarity, and using that as your initial concentrations. Once your initial concentrations are determined, then you can come up with your equilibrium expression. So here we have another problem. Buffer prepared by 0.25 molar ammonium with this Kb and 0.4 molar ammonium chloride. Find the pH of the buffer. So we have simply setting up the buffer here. We have just like regular old equilibrium before, but we have our base and its conjugate acid. Okay, so this is in name a buffer. You could have done this during the acids unit though. We have our values plugged in, neglected x's, a concentration for hydroxide ion, and then negative log of that gives pOH, subtracted from 14 gives 9.05 for that pH. Please peruse that if you feel the need. So here we are going to use that same buffer when 0.5 moles of gaseous hydrochloric acid is bubbled through 1 liter of our solution. 1 liter of solution. Okay, so since it's 1 liter, we're blessed here. 1 liter allows us to take these equilibrium or these initial values that were in molarities and say, well, then that's just moles also, isn't it? So here you go. You have 0.1 mole of acid being added in. We had 0.25 moles of ammonia and 0.4 moles of our conjugate acid ammonium. we realize that there is 0.1 moles of hydrogen ion and 0.25 moles of ammonia, and we would react all of our hydrogen because we'll have excess ammonia, and that will leave us with 0.15 moles of ammonia and 0.5 moles of ammonium. Note, you have to add what you create on the product side. This is often forgotten. Please be diligent. So once you have those values set, you can plug them into your equilibrium expression and solve for POH. Subtracted from 14 gives 8.73. Henderson Hasselbalch could be done right there the same exact way. Pretty remarkable.